Good afternoon, everyone. Thank you for being here today. My name is Xiaoyue, and it is my honor to represent my co-author, Professor Lannan and Professor Qiang Zeng from George Mason University to present our work titled From 1,000 Pages of Specification to Unveiling Hidden Bugs, Large Language Model Assisted Fuzzing of Matter IoT Devices. To begin, let me talk a little bit of Matter. Matter is a new open standard for IoT devices backed by over 200 companies, including technical giants like Amazon, Google, and Apple. Matter aims to provide a uniform standard for IoT devices. That is, for example, a Google Hub can control an Amazon plug and vice versa. Given the popularity of the Matter, discovering the bugs and the vulnerabilities in Matter device is an emerging important problem. The existing IoT fuzzing approach, such as firmware emulation, hacking companion apps, and collecting vendor test scripts, all come with a significant drawback. They require per-device effort. This means each device needs to be individually set up and individually tested, which is not only time-consuming but also limits scalability. Our key insight is that any Matter device can be controlled by a Matter controller. Leveraging this, we designed a method named controller-based fuzzing, where we send testing message from a controller to the device. This approach is inspired by our previous work, Fuzzer, presented on MobiCeS 2023. Notably, our method do not require the emulation, hacking companion apps, or collecting testing scripts. This significantly reduces the per-device effort and allow a more general testing process. We observed that Matter specification itself contains extensive and detailed information, such as valid parameter values, command effects, and expected responses. It is a promising approach to make use of the rich information in the specification to generate the test inputs. However, there are some challenges. We identified four primary challenges: how to scale the command coverage inside the device, how to deal with the shared vacuum of the specification, how to find the stateful bugs and non-crash bugs besides to the traditional crash bugs. Let us talk about command coverage inside the device first. This challenge is we want to ensure that our fuzzer tests all the commands supported by a device. Our observation is when a controller adds a device, the device declares all the supported commands. Thus, we build a fuzzer within a controller first and extract the supported commands from the pairing process. As mentioned earlier, the Matter specification has extensive and detailed information. It is not surprisingly that the specification contains over 1,000 pages. Manually pairing the specification from human-readable content to machine-readable content would be a time-consuming task. Besides to the sheer volume of the specification, commands only make sense when a device is at a specific state, which can be represented in a finite state machine. To address these challenges, we employ a large language model to assist us. The large language model can help us transfer human-readable content in the specification to machine-readable content. Furthermore, the machine-readable information includes the device states, commands, and their relations is represented in FSM. However, here we represent an example of a finite state machine for the level control cluster, which illustrates how commands interact with a device state. The node is a device state, and the edge is a representative of the execution of the command. By utilizing this information, we can better identify and test stateful bugs. In general, we cannot modify the firmware and install the alternative firmware in the IoT devices, since almost every IoT devices has code signature checking about the firmware. Thus, it is feasible to collect the program execution information inside the device. We cannot collect the branch coverage, path condition, and function return values. To handle this, we propose to leverage command semantics. For instance, if the execution of the command is expected to modify the specific device attributes as they described in the specification, our fuzzer queries the corresponding attributes. If the command is meant to be rejected, an error message is expected. To improve our fuzzing process, we have developed the finite state machine guided test generation policies. For instance, we test for invalid values extract from the specification, provide non-inputs, and provide unexpected data type, and so on. In this slide, I show an example of the bug. We changed the normal payload from 1 to 0. And we also changed the normal payload from 1 to non-inputs and changed to different data type. 0 is a special value listed in the specification and described as the device should reject this command and respond with invalid command. Our evaluation involved testing 23 Matter devices, include a smart switch, light strip, locker, sensor, and hubs. Though our fuzzing approach, we discovered 147 new bugs, include 3 CVEs. None of these bugs could be found using snippets. The snippet is a priori state-of-the-art IoT fuzzing tool. Let me share a specific example of non-crash bug we found. In this case, a go-wait light device strongly accepts the command and execute. This bug is a state-sensitive bug, which is the bug only works at the specific initial state. The initial state of the device is the highest queue. We expect the device reject the command and responds with invalid command, but instead it changes state unexpectedly. In summary, our research introduced the first MetterFuzz and mGPTFuzz. These two features a controller-based fuzzing architecture, and we leveraged the large language model to assist us in fuzzing process. We targeting stateful bugs and non-crash bugs. Our effort led to the discovery of over 100 new bugs, including 61 zero-day vulnerability and 3 CVE. Thank you for your attention. I will appreciate if any questions or comments you may have.